Welcome back to another episode of Dave Does Math from Home. Today we're finishing part 2 of our section on planar vectors, the first section, Calc 3, so hopefully you're enjoying Calc 3 so far. I ended the last video pretty abruptly with a mention of the word scalar and then tormenting a cat. So I want to talk a little bit more about scalar, but before I do that, I want to talk a little bit more about magnitude. So in the first video I said that vectors have a direction and a magnitude. The direction, you can find the direction, like we talked about how they're vaguely sort of similar to polar coordinates in a way. When we were finding polar coordinates for rectangular things, we realized we could find the direction using an arctangent, and that's still true. If you're really curious about the angular direction that a vector points, you can use an arctangent to find that angle. I'm not actually going to do that. It turns out that knowing that number in degrees is almost never very important or relevant for calculus. Like having that number as distinct x and y values, there's a direction implied, but knowing the exact degree measurement of it is sort of never important in this class. It was still important when we did it in pre-calculus, because lots of people need to know that stuff. But for us, we're not going to pay attention to degrees much. But we are going to talk about the magnitudes. So we said that magnitude is like the size of the vector. If you're dealing with a position vector, it is the distance that you travel. If you're dealing with a force vector, it's the amount of force that that vector is applying. Vectors get used a lot to model the flow of things. So if you want to imagine like a stiff breeze, a strong breeze could be represented as sort of like a field of vectors that are all pushing in one direction with a certain amount of force. And if the breeze dies down, then that magnitude would be diminished. It would be smaller to represent a smaller force that's pushing. So there's a lot of utility in thinking about these things as sort of directions and magnitudes. But I want to talk about how to get those magnitudes. And we'll start with vector v again. V we said was 3, 4 in little triangular brackets, which meant that it was this vector from 0, 0 to 3, 4, or you could move it around from anywhere else you want to anywhere else you wanted. Where exactly it is not important, as long as it has these dimensions, +3 and then +4. That's what makes it vector v. So we can find the magnitude of v. Is written with sort of these double brackets. Kind of looks like a double absolute value sign, and it's meant to, because it has a lot to do with absolute value. When we were doing pre-calculus, we said that the absolute value of a point. When we were doing pre-calculus and we worked with complex numbers, that's where I'm going with this. We said that the absolute value of a point on the complex plane was its distance from 0. And that's sort of the idea we're going with here. The magnitude of a vector is its distance, its size. And we're going to find it in the exact same way that we found the absolute value of complex points on the complex plane. We're just going to use the Pythagorean theorem. The square root of 3 squared plus 4 squared. And that's it. So in this case you get 5. And now the really cool thing about this as a magnitude is we can talk about the magnitude of 2v, which is the absolute value of 2v. In this case, we're going to need to do the square root of the two components squared. So the two components of 2v should be 6 and 8. So we'll have 6 squared plus 8 squared, which is 36 plus 64 is 100. Square root of that is 10. So here's the good news, the really good news about this. The magnitude of 2v is twice the magnitude of v. So if you were hoping that it was going to work out like this, you were correct. It does work out like this. And that sort of brings me back to why these are called scalars. They're originally called scalars because they scale these vectors. If you want to multiply something by 2, you get something that's twice as long. Exactly. If you want to multiply something by 1/2, you get something that's 1/2 as long. Exactly. If you want to multiply something by -1, you get something that's exactly as long, because magnitude does not care about direction. Magnitude is just the size. It doesn't matter which way it's pointing. Multiplying by something by -1 will change the direction it's pointing, but it won't change the size. You'll still get the same magnitude here. So these things are called scalar multiples because they scale the vector up and down. And as sort of an extension of that, scalar has sort of become the word to describe any number that's not a vector. So when we're dealing with vector arithmetic or vector mathematics, we're going to have a bunch of stuff that's vectors, like v and u. Those are all vectors. And the word scalar means literally anything that's not a vector. So this 2 is a scalar. If we multiply something by 8, that would be a scalar. And mostly they're going to be used as multiples, but they're all called scalars. The last thing that I need to talk about in terms of scalars and v is the idea of a unit vector. Hopefully we remember from pre-calculus what the word unit means. Unit fundamentally means 1. It means 1, especially with respect to size. I'm getting really liberal with these abbreviations here. This is especially with respect to size. Hopefully you remember that from talking about the unit circle. The unit circle is called the unit circle because it has radius of 1. And that 1 is the unit. So, accordingly, a unit vector is a vector with magnitude equal to 1. Which turns out is pretty easy to get. As we move forward into more vector math and then eventually vector calculus, it's going to become pretty important for us lots of times to be able to get unit vectors for things. So the unit vector is what happens when we sort of take away the magnitude of something and only look at which direction it's pointing. We're sort of normalizing all of the sizes of all the vectors involved at 1 so that we can only compare various directions of things. And we get that by just dividing by the magnitude. We said that v had a magnitude of 5. So unit v, this is how I write a unit vector. I don't think the book does this, but this is my version. Unit v is the vector v divided by the magnitude of the vector b, which in our case will be 1/5 of 3 comma 4, which is 3/5 comma 4/5. That's not a good bracket. So this is a neat trick. You can always turn any vector into a unit vector by dividing it by its magnitude, or multiplying it by 1 over its magnitude. If you want to verify that this is a unit vector, you can find its magnitude. I would welcome you to try that. I'm not going to try it on this video because I'm out of things to say. Stay tuned for the next one. The next one is vectors in space.